hello everyone. We will continue with our lecture number 26 this time. So, last lectures we have reviewed calculus of variation concepts, as well as we have seen how to use it for optimal control formulations, and that we discussed about some examples and all, and we also discussed why those problems are difficult to solve in general, and then there is a necessity for solving those in a computational manner actually. So, we will see those couple of those traditional classical computational methods in this lecture. The summary is this summary of this necessary conditions of optimal control is something like that. We all derived it last time. First thing, it throws some necessary conditions of optimality as three major equations. One is the state equation, co-state equation, and the optimal control equation. And we discussed last time that the state and co-state equations are dynamic equation. You see a dot there. Okay, this is n-dimensional differential equation. This is also n-dimensional differential equation. So, these are differential equations, whereas this optimal control equation is normally a stationary equation or a static equation actually. So, that means in principle you can solve u as a function of x and lambda from here. Either this can be solved explicitly, okay. That means the nature of this equation allows you to solve u explicitly as a function of x and lambda, or it may so happen that you may also need some numerical method to, like Newton-Raphson or something, to solve this equation in a computational manner, in a numerical way also. So, but the main problem here in this entire difficulty comes from the fact that this state equation boundary condition is given at initial time, except T0 is available to us, whereas the boundary condition for the co-state is available only at final time. Okay. That means n boundary conditions are available at initial time, whereas n boundary conditions are available at final time, and you have a 2n dimensional differential equation basically. Okay. So, that means we are left out with a condition where we have to discuss this 2-point boundary value problem actually. Okay. So, differential equations are 2n, n conditions are available at the initial time, n conditions are available at the final time. That is the major problem actually. Suppose we knew every boundary condition at one point of time, either initial or final or somewhere in between, things like that, then we could have simply integrated the differential equations either forward or backward. Okay. But since we do not know that, half of the things are here and half of the things are there, we certainly need numerical intensive procedures to solve this actually. So, let us see how do we do that. So, these are some of the things I just discussed, the salient points of these necessary conditions of optimality, that the state and co-state equations are dynamic equations. State equation develops forward, whereas co-state equation develops backward. The optimal equation is a stationary equation. You may or may not be able to solve it in an explicit manner. If you cannot, then you can again use numerical procedures to solve that. And the core of the point is this entire formulation leads to this so called 2-point boundary value problems, which demand computationally intensive iterative numerical procedures to obtain optimal control solution. So, we will see what are those actually. Okay. All right. So, in this lecture we will study three classical methods. Okay. These are very heavily used in many industries, especially in aerospace industry, and these three methods have their own advantage, drawbacks and things like that. We will not talk too much on those aspects. We will see how do we use these things actually, how can we use these methods in practical problems like that, what are the methods, what are the procedures and all that actually. Okay. So, first we will discuss about what is called a gradient method, the second we will talk about suiting method, and the third we will talk about something called quasi-linearization method. Okay. So, probably they are of like increasing order of complexity, but then once you understand that and try to implement, then probably the more complex the algorithm is, the convergence properties are better and things like that actually. Okay. So, just keep that in mind. Okay. So, gradient method. Before I move on to any method, by the way, all these methods will assume that we have to guess a initial condition for the control. That means, we really need to guess a control history from T0 to Tf. Okay. Then we need to update that control history as the iteration proceeds actually. That is the core of the matter in any method actually. So, you need to really guess some control history, and that is typically not trivial by the way. That means, if you really want to guess a good control history, then you should understand the physics of the problem first, and based on that some intuitive design or some some heuristic design you can do to get a good control history actually. And also remember, these are necessary conditions, and then you have to be slightly careful about that. In other words, whatever is your guess history that you are talking from T0 to Tf, around that the control may stabilize actually. So, let us try to understand that concept a little. Okay. So, suppose you have this this time T0 to, let us say, T0 to Tf, okay, and you have this u of t, let us assume it is scalar. So, this is, let us say I have guessed this history basically, this control history. Now, what will happen here is, if I guess this control history, most likely my final control is also going to stabilize around that basically. Okay. So, this is let us say my guess, okay, and this is my final. Okay. Now, suppose I guess some other thing for the same problem. Okay. Let us say suppose I guess some other thing for the same problem T0 to Tf. Okay, let us say this time I guess something like this, then my solution convergence may happen something like this. Okay. That means, this is, let us say, my guess history of the control, this is my final actually. Okay. So, just be careful that while you are guessing, your guess control also relies on certain heuristics, certain signs, or at least stabilizing control or some other control design that is not optimal, things like that. And then whatever guess history you are feeding to the control design, most likely you are going to get a solution around that actually. So, guessing that procedure, guessing procedure itself is a heuristic science by itself actually. So, be careful about understanding the physics of the problem while applying some of these methods. Try to utilize some guess in the beginning, and then you update on that. For example, missile guidance problem in aerospace, typically the guidance problem, very classical guidance law is proportional navigation Pn. So, if you really want to find out an optimal guidance law, non-linear optimal control based theory based guidance law, then probably you would like to guess a lattice history using Pn guidance, and then using that lattice as a guess value, you can try to update your thing actually, update your lattice value. So, they are subjective to the problems actually, just keep that in mind. Alright, so let us proceed further. We will talk about gradient method first. Okay, in the gradient method, out of these three equations that we are having, okay, so what you are assuming is that state equation, co-state equation, optimal control and things like that are available. So, what you are assuming is that out of all the conditions, remember if any of the condition is not satisfied, then it is not optimal control actually. Okay. So, out of all these conditions, we will assume that state equation is satisfied, co-state is satisfied, as well as boundary condition is satisfied. What is not satisfied is this one, okay, with respect to the guess solution actually. Okay. So, we have guessed a control history, and with respect to that guess, that is certainly not optimal, we want to make it optimal. But with respect to that guess, we are assuming that state equation, co-state equation and boundary conditions all are satisfied. And then what is not satisfied is only this condition, and hence that is a non-optimal control solution. We want to make it optimal by successive enforcement of this condition actually. So, that is what our strategy. So, let us see how do we do that. Okay. So, that is what I told, state equation is satisfied, co-state is satisfied, boundary condition is also satisfied. So, what is the strategy? Strategy is successively do some successive iterations, so that our optimal control equation will also be satisfied actually. That is the strategy there. Okay. So, now go back to the derivation part of it, what we discussed last class. So, we derived this expression del j bar is the augmented cost function, remember that, and we wanted to make sure that this is equal to 0, and hence all these coefficients needs to be 0, and that is how we derived these necessary conditions actually, remember that. So, now what we are telling here is, okay, because state equation is satisfied, let us say, because our assumptions one by one, let us say. So, the boundary condition is satisfied. So, this is 0, okay, this is gone. State equation is satisfied. So, this is gone, this is x dot equal to f of tx basically, and co-state equation satisfied, that is also gone. So, what is left out is only that part, that is left out actually. Okay. Okay, so only this part that is left out actually. So, let us see how do we make sure that. So, what this gradient method tells is, once this once these conditions are satisfied, we are left out with del j bar is that, and you want to make sure that del j bar decreases in successive iterations actually. Okay. And remember j bar is nothing but a positive quantity actually. Okay. J bar itself is a positive quantity. So, you want to make sure that the del j bar is negative quantity basically. So, that successive iteration it decreases and ultimately stabilizes somewhere actually. Okay. So, j bar turns out del j bar, the first variation of j bar, you are having only this term. Okay. Now, let us select that del u is something that we need to select, that is the one that we need to update, remember that. So, u already we have some u basically. Okay. This is what is del, I mean by definition this is what is del u basically. Okay. This difference actually what you see here. Okay. So, this difference whatever thing you are looking, okay, this difference is something that needs to be found out actually. Okay. That is nothing but del u bar, I mean del u basically. So, that del u is something that we were interested to find out, and now let us propose that the del u will select it that way. Okay. So, negative of del s by del u with some learning factor tau which is greater than 0 basically. Then what happens? Then if you plug this one back here, you are left out with some term like that, which is certainly a positive quantity. Remember del s by del u is a vector. So, it is something like x transpose x sort of thing. So, it is certainly a quadratic term inside. So, this quadratic term inside is certainly positive because every term is square addition of squares actually. And then if you have a negative sign associated with that, tau is a positive quantity anyway. So, del j bar becomes negative actually. Okay. So, you have a positive quantity for which the del j, I mean j bar is a positive quantity, where del j bar is enforced to be negative actually. Okay. So, that is how we make sure that the j bar decreases actually. So, we are talking about a minimization problem here. Okay. So, if it is a maximization, you do the reverse thing actually. Okay. So, for a minimization problem, this is the variation that you need to select actually. That means, at any point of time t k, let us say, then I will evaluate del s by del u at that time t k, and that is my del u k basically. Okay. So, I will update my control based on this del u k basically. That is how it happens there. Okay. So, that is what we are doing here, that if you observe this expression, we are okay, del u I, let us say that is what at ith iteration sort of thing. Okay. It is actually like by definition it is del u I nothing but u I plus 1 minus u I in that iteration sense, this is nothing but that minus tau times del s by del u ith iteration of course, and then this lead to this condition that u I plus 1 is nothing but u I minus this thing actually. So, and this is also, remember, this is a negative gradient direction actually, which is also like incompatible with what we know in static optimization numerical methods actually, steepest descent method, and then also like that is also called gradient method actually anyway. So, this using this gradient, okay, gradient is what? Gradient of Hamiltonian with respect to control. Okay, that is what you are using. The variation or change in control that you are looking for is nothing but negative of some learning factor multiplied by gradient of H Hamiltonian with respect to u, and that is why this name gradient method comes actually. Okay. So, that is what we need to do, and ultimately del j bar turns out to be like that, which is guaranteed to be less than equal to 0, and eventually del j bar, because it is successively decreases and j bar is a positive quantity. So, ultimately del j bar will stabilize at 0, and that is what we want for optimal control. Remember, once we how to derive this, ultimately we want this del j bar to be equal to 0, right. That is what we ultimately want. Okay, so that is why, because these are already 0, we are assuming that these are 0 anyway, and that is what we are assuming, that we are ensuring that that is also 0, and hence this everything becomes 0 actually. Okay. So, that is what you are doing there. Okay, so what is the procedure now? Okay, in gradient method, we need to assume a control history. Again, it is not a trivial task. We need to have a good understanding of the physics of the problem to come up with this good control history, okay, to start with. And then once we have this history in place, then what we do, we integrate the state equation forward, because remember initial condition for the state equation is known to you, now control is also known to you. So, if you go back to the state equation that we started, once we know a full control history u of t, and we know a initial condition for x 0, this equation can be integrated forward. So, you can keep on integrating this from t 0 to t f, because every time you have a control value known to you basically. Okay. So, the at t equal to t f you will find some xf value, okay, and based on that xf value you can evaluate this fellow lambda f equal to del phi by del xf, right, because phi is a function of t f xf only. So, del phi by del xf is available to you and t f is anyway available, and by integrating this equation forward you also know xf value. So, this equation can be evaluated now. Okay. Now, what happens because you know the final condition, final boundary condition for lambda, you have this differential equation anyway. So, you can integrate this equation backward actually. Okay. So, once you have this equation can be integrated forward and this equation can be integrated backward actually. Okay. So, then while doing this backward integration you have two choices. You can either keep on updating your control based on this whatever you are proposing here, based on this update what you are doing, okay, you can update this control first and then integrate one step backward and then keep the process going that way, or sometimes people update the control history fully from t f to t 0, you can integrate the entire lambda history first and then update the control history everywhere. Okay. So, that is there are two choices with you actually. Okay. Okay, let me summarize again. You start with a control history guess. So, you have this x 0 known to you. So, then integrate this state equation forward, then you have xf available. So, because based on that you can evaluate lambda f. Now, once lambda f is available you can in principle integrate this equation backward. As remember this control history is available to you, x history is also available to you by now, and then this is also lambda history also is getting available because you are integrating it backward. By the way, there is a small print mistake, this is also a function of lambda in general. Okay. This is it is a function of t x u lambda everything actually. Okay. So, this part. Okay. So, that is what so you can once you know lambda f, then this equation can be integrated backwards and you can integrate the entire lambda history backward from t f to t 0 and then think about updating your control history everywhere from t 0 to t f, or we can do it one at a time. In other words, you update the control once and then integrate the co-state equation 1 delta t, update the control history again at that particular point of time, then integrate it 1 more delta t, like that actually. So, the choice is based on the user, whatever you want to do you can do actually. Okay. So, this is what you are doing actually. Okay. Now, this is gradient method. Okay. So, this is all that procedure that I am writing here, I have written here. Integrate the state equation forward and then integrate the co-state equation backward and update the control solution. Okay. That means, again this can either be done at each step while integrating the co-state equation backward, or after the integration of the co-state equation is complete. So, either the choice is yours actually. And you have to repeat this procedure until convergence. Until convergence, obviously you cannot expect that del h by del u is exactly equal to 0. You have to stop somewhere in a very small tolerance value sense. So, this is one of the candidate. Del h by del u transpose times del h by del u is a quadratic term integrated from t 0 to t f. So, that entire scalar quantity should be less than equal to certain pre-selected constant, small constant value gamma basically. Okay. So, that is where you stop and then you tell, okay, that is where we got my optimal control actually. Now, there is this there is a small dithering here and a small ambiguity. How do you select this value tau actually? Okay. Now, the idea is this tau can be selected, okay, either pre-selected. In other words, if you, okay, this needs to be typically 0 and 1, it is never greater than 1 also. I mean, sometimes people use that very small value greater than 1, or initially you can start with a larger value and then while you go towards optimal value, this tau needs to be reduced actually. Okay. So, that way the convergence properties are fast and things like that actually. Now, one can also think, okay, I will fix a small value of tau in the beginning to end. Then what happens is you have a slow convergence process. Convergence is not fast actually. Okay. And if you have a larger tau value, then it jumps, it oscillates around the optimal value actually. Okay. It will never converge in a very good way. So, one procedure tells us that, okay, tau I can select initially slightly higher, let us say 0.9 or something, then gradually I will decrease as my iteration proceeds. And then finally, I will see that condition is met, this tolerance condition is met ultimately actually. Okay. That is a procedure that is a strategy. Other approach, other idea is something like this. You can select a tau, okay, so that it leads to a certain percentage reduction of J bar at every iteration. Okay. That means, let us select a tau, or we can aim to select a tau, that every iteration when I do, then this J bar value is going to reduce by certain percentage, let us say 10%, 15% like that actually. So, that let that percentage be a number be alpha. Okay. Then what it tells you, these are that del J bar, what is left out here, okay, that has to be equal to certain percentage of J bar that you already have actually. Okay. So, that means alpha by 100 into that actually. So, that way you can compute a tau based on this actually. You can solve for tau from here, and that is your tau value actually. So, sometimes this procedure helps you, and these are all subject to all numerical procedures will also contain some degree of art, which are problem dependent actually. So, as you work on these any of these problems, you will get more and more experience, and then you will intuitively feel how to select a proper value of alpha and tau and things like that. Alright, so that is the procedure. Now, let us go through a little real life challenging problem out here. Okay, remember last time we have seen some classic classroom sort of textbook examples and all that. Now, this is a problem that I have taken from literature. Okay. So, the problem is something like this actually. Now, what happens is normally in air to air combat, okay, they are like an aerospace problem sort of thing. You have a carrier aircraft. Okay. Typically, you launch a missile, okay, for a target that is in front actually. Okay. So, that means, if your target is somewhere here normally, okay, you launch this missile somewhere here. Okay. So, it is going to go and engage very far away, it is not very close anyway. Then what you do is the aircraft takes a turn and goes away actually, it does not go to the target because target can kill it actually otherwise. Okay. So, that is normally what is done. Okay. But what you are interested here is not like that. Okay. Let us say the target itself is in the backward hemisphere. Okay. It is not in the forward thing. Okay. So, how do I, but I can carry a big sensor in my aircraft, okay, which will look both forward as well as backward. I can set up a set of sensors actually, which can identify that there is a target in the back side also. Let us say an enemy missile or enemy aircraft or something like that actually. Okay. Then the idea here is, if I take let us say I can take half of the missile on my wing, the aircraft has only limited space. So, you can take half of the missile which will look forward, which can be launched forward, and half of the missile which can be launched backward. Okay. That is a choice, but once you have that choice, the combat capability reduces, because you never know how many targets are in front and back, and if the backward can attack only backward and forward can attack only forward, then certainly your capability is limited actually. So, what we really need to do is, we will take all the missiles in the frontward direction only in the wing, and then depending on the situation we are going to launch those missiles in forward direction only. So, launching direction will be certainly forward. Now, if the target is backward, then this air launched vehicle is supposed to turn back and attack actually. So, once it turns back, then only its own seeker and its own detection mechanism can look at the target. Until that, it will not be able to lock onto the target actually. So, the first primary task is to make sure that this one rotates by 180 degree. After launch, the aircraft after launch, the aircraft will go that way. Okay, let it go that way, and the missile will come that way and then try to attack the target actually. Okay, so that is that's the problem actually. So, the first thing what we want to do is, after launch the missile should turn by 180 degree. Okay, so that is what our main aim, and especially when you talk about missile guidance problem, we are more interested in turning of the velocity vector, not the turning of the attitude itself. But if once you assume the small angle of attack and all that, then velocity vector and attitude are almost parallel to each other actually. So, they are same basically, direction sense. Okay, so we will not discuss too much on that. What we are telling here is, we will launch this velocity vector in one direction. Okay, it is all about velocity vector only. It is nothing to do with missile orientation per se, and attitude is not considered here. So, we launch it in forward direction, and then this is supposed to turn back and see the target. After he sees the target, the problem is over anyway. So, our problem is to turn the vehicle from 0 degree to 180 degree. After that, how it engages and all, it is a separate problem, it is a problem by itself actually. It is possible to do certainly. Okay. but first primary task is to turn it by 180 degree actually, and typically you want to turn it by minus 180 degree, because you do not want to, because this air launched missiles are typically carried under the wing actually, it is not carried over the wing. Okay. If it is under the wing, then the aircraft goes that way, then certainly it is safer that the missile turns in the downward direction, otherwise there is a chance that it may hit our own aircraft actually. So, obviously we want to avoid that. Okay. So, it has to turn it by minus 180 degree and then lock onto the target actually. Okay. After that it can be guided by its own homing guidance logic actually. And you can also see that every other case can be considered as a subset of this extreme case basically. Okay. That is what it is. So, these problems are given in detail here. So, what you are telling is you are primarily interested in Mach number and gamma. Gamma is the flight path angle, Mach number is velocity of vehicle divided by speed of sound in that medium basically. Okay. So, we have this typical laws here, and also we know that these equations are given in terms of non-dimensional quantity, even including time. Time is also non-dimensionalized. Some non-dimensional parameters are like that. Typically, these non-dimensional things helps us to write generic formulations actually, because this is not very specific to missiles anymore, that particular missile anymore actually. All the variables that you see here are all generic non-dimensionalized quantities actually. Okay. So, what is the idea here? Now, you cannot waste your time while turning. So, this turning should happen as quick as possible. So, certainly it is a minimum time turning problem actually. So, that means my cost function is like this. So, my Tf minus T0 or Tf minus 0 rather, whatever, it needs to be minimized actually. Okay. And the constraints that acts on the vehicle, initial flight path angle is 0, final flight path angle needs to be minus 180 degree, initial Mach number is known to us, and let us say the final Mach number we want it as 0.8 actually. So, we do not want too much of velocity drop either. While this turning happens, the velocity drop should not be very high actually. So, we want specific final value of the Mach number. Okay. That is 0.8 actually, let us say. So, this is what you are talking, they are all non-dimensional quantity, m dash is dm by d gamma. No, what is going on here is m dash and gamma dash is with respect to tau, which is non-dimensional time. Now, conveniently what is done here, okay, is an innovative way sort of thing, because minimum time problems are typically harder problems to solve. Okay. You can see that L equal to 1 here, and then you take the H equal to that 1 plus lambda transpose, things like that will happen. And then when you take del S by del U, you may not get anything to solve for control actually. Okay. So, it has to be done in a different way, and there are procedures to do that. This typically goes through this bang bang control and all that actually. So, we will not discuss too much on that actually anyway. But coming back to that, what is done here in this particular literature very interestingly, that this change of variable the authors have proposed actually. So, in other words, I do not want to visualize this equation in terms of tau or non-dimensional time, but I want to visualize as function or differential equation in terms of free variable as gamma. Okay, gamma is the flight path angle actually. So, if it is free variable as gamma, then dt by d gamma I can write 1 over gamma dot actually. Okay, so, that is 1 over gamma dot expression. Okay. That means gamma acts as a free variable here, whereas t acts as a state variable here. That is a little different way of looking at the problem actually. So, if I j is something like 0 to t f dt, then it is equivalently it is 0 to minus pi dt by d gamma, and dt by d gamma expression is available here. So, that is put here actually. Okay. So, you have a cost function which is no more 1 inside here now. Okay. And the limits of integration has taken care of this 0 to minus pi, these are all limits for pi that you want actually for gamma. Okay. That is what you want for gamma basically. So, that has taken the limits now. Okay. And here what you are putting is dt by d gamma into d gamma. So, dt by d gamma into d gamma is nothing but dt. Okay. So, this change of variable we are not compromising the goal, you are still solving a minimum time problem anyway. But while changing that, the problem appears in terms of gamma, which is 0 to minus pi and things like that. Now, subject to only one differential equation here, dm by d gamma, because this part has gone inside the state equation. So, what was initially a 2-dimensional problem or 2-dimensional states and all, it is now converted to a 1-dimensional constraint problem with these hard constraints in place through these limits of integration, and this is what we are talking about a minimum time optimization problem actually. Okay. Now, you can use your generic theory and then you can actually try to solve this problem, and this is a task that I am giving you. If you are interested to solve this, the task is you try to use this gradient method and try to solve this problem for initial condition of Mach number is 0.5 and the engagement height at 5 kilometer, things like that. And you can finally take the some of these parameter values, which are again representative numbers, I mean just to have a feeling of what is going on, certainly not with respect to any particular vehicle per se. Okay. This is not really m2, this is actually m square, obviously meter square basically. Okay. All right. So, this is what you need to do. So, my task that I am giving you is you try to experiment the gradient method based on these numbers actually, and you, on the way you may need some atmosphere data and all, because that is where you need to compute dynamic pressure, and you can use some standard atmosphere. There are international standard atmosphere, US standard atmosphere, Indian standard atmosphere, like that actually available. So, you can take any standard atmosphere to compute air density as a function of height, and then you can you are ready to work on this problem. This is your cost function what you want to minimize, these are the bounds or limits with respect to gamma, and the state equation that is coming along with this cost function is only this one actually. So, you derive the necessary conditions and then you can talk about solving this this problem for with respect to these parameters in place actually. Okay. So, that is this is a representative of this some aircraft to air missile sort of thing, but it is certainly not with respect to any particular vehicle. I have just given these numbers for experimentation and then having a feeling of what goes on actually here. Anyway, so that is what it is. Now, let us go to the shooting method, the next one. So, what we are doing here is again revisiting the same problem. Okay. So, that is but we want to have a different method here actually. The problem is exactly same, state co-state equation dynamic, optimal control stationary, you have split boundary condition, half in the initial time, half in the final time. So, let us see how do you do that. Now, this particular method assumes that whatever control history that you guessed is like shooting a gun to the target actually. So, suppose you want to shoot a gun to the target, then initially you aim something, it obviously does not fall on the bullseye, it does not fall on the target directly, but after it falls somewhere you know how much it has travelled and things like that. So, that means let us say pictorially, suppose this is somewhere here, I try to fire a target something, I mean some stone something like that, it has gone fall somewhere actually. Okay. So, this is my actual position where I left, where I landed, but this is where I should be basically. So, there is obviously this error is available to me. So, using this error I will update my control history in such a way, or let us say in this particular case this initial launch angle, that is what you are telling. Now, using this error information I have to revise my launch angle in such a way that okay, next time I will do something like that, closer to that. Okay. Now, next time I may overshoot actually, okay, that is fine. So, yeah, then you can, I know that there is a solution in between. So, every time I use this error information, that is where I should be and where I am falling at t equal to Tf, and then using that information, okay, I will come back and try to update my control history actually. So, that is like shooting, where you are initially shooting and it falls somewhere, then again you go back and shoot in some other direction, fall somewhere, I mean again falls somewhere, it may be closer to target, but not on the target, and then you try updating this control or guess whatever you are telling, initial guess, then you proceed further. Now, in this procedure we are assuming that initial guess for lambda is known to us. Remember that if all conditions are known to us at n in t0 or any particular point of time, then you are okay, you can integrate the equation together, but because that is not happening. So, what you are telling is okay, let us hold our breath for this one for a second, we will not consider this this boundary condition for a second, okay, but we will rather assume that lambda of t0, okay, is available to us. Okay. Okay, so that is available. So, x of t0 is available, lambda of t0 is available, then together it is available. So, I can certainly integrate this stated co-state equation together, both in forward direction only. Okay. Now, once I update, then ultimately I will get an xf, and then I can evaluate with respect to that xf, I can evaluate my lambda f, and that lambda f may not be kind of same, because this update will throw me some lambda f, whereas my correct lambda f should come from this equation actually. Okay. So, that will throw me some error in lambda f, and using those error in lambda f, okay, I should be able to correct my initial guess of lambda what I am talking actually. Okay, so that is the procedure. So, it demands that I start with an initial guess value of lambda vector, and also remember that lambda is a constant variable, does not have any physical meaning. So, guessing that again requires that you guess a control history from T0 to Tf and then integrate once forward and once backward, and then whatever the constant equation you integrate backward, it will give you a correct value of lambda T0 guess actually. So, still you required a control history guess basically. So, that you cannot get rid of that. Okay. Now, sorting method is something like that. I have guessed this lambda 0. So, I form a metastate vector x and lambda. Okay. Then this implies that there is dz, the error in this metastate vector is also dx d lambda actually. Okay. So, I guess lambda T0, so x T0 is given anyway. Okay. So, this leads to this equation that lambda dot x dot and lambda dot together if I see, that is z dot is nothing but f of z, and z of T0 is now available. So, I can integrate this equation by forward together basically. Okay. And simultaneously I also have an error integration, error equation dz is equal to dx dot d lambda dot, and f z dot is that. So, if I consider this linearization and all that, then dz dot is nothing but del f by del z into az. Remember, del f by del z is nothing but something like a matrix that we know actually. Okay, this is something like A, but unfortunately this is actually a function of time, that is it is actually it becomes something like a time varying A matrix actually. Okay. So, that is where this is the error equation is a linear equation that we are interpreting, but it is a time varying linear equation. So, to solve that we need this concept of state transition matrix actually. So, the state transition matrix for dz, this equation is given something like this, that is the state transition matrix. Okay. This state transition matrix, and this state transition matrix we know that it satisfies the same differential equation. So, we can this in a matrix sense actually now. So, this from this equation this state transition matrix equation is also known to us, phi dot is equal to del phi by del z into phi. But the good part of it is phi of T0 T0 is identity. That means, this equation that you are having here for phi, okay, this is independent of my problem description that I am talking actually. Whatever problem, whatever initial condition, it is independent of that. So, that means, this integration of this phi equation can be done independently. That is why the state transition matrix concept is actually useful. Okay. So, I increase that, but also remember that the dimension of this phi matrix is 2 by 2n by 2n actually. So, even if you are talking about let us say symmetric matrix and things like that which may or may not happen, then you talk about still you are having some n into n plus 1 by 2 elements free basically. So, that many differential equations you have to integrate and things like that. Okay. So, in general this is a large dimensional matrix, and hence this is a large dimensional differential equations, so you need to integrate actually, that is where it becomes computationally difficult, intensive basically. So, what you are doing here is you will integrate this equation, okay, as well as this equation, and then you are ready with this optimal control you need to keep on solving on the way basically. Okay. Now, that is this equation still needs to be solved. Okay. So, that is what you are doing here. Okay. So, you numerical integrate equation number 2 and equation number 4 while solving this optimal control u at each instant of time actually. Okay. So, that is this optimal control equation needs to be solved at each instant of time. So, that is what you are doing here. And finally, what you are getting at t equal to Tf, we are getting dzf is something like that, that is our ultimate aim. But also remember that these state transition matrices are never singular. So, I should be able to invert this and then try to get a value of dz0. That is where I got my d lambda 0, that is the correction that I need for lambda with lambda 0 basically. So, that is my ultimate aim. I started with some lambda 0 guess, and then I want to update this lambda 0 actually. So, this is my lambda 0 that I am looking for. Okay. So, d lambda 0, and then obviously you require half of this matrix only, because dx0 is something that we do not want to utilize, because x0 is fixed anyway. So, dx0 we forcefully put it as 0, even though the computation computes something, we do not want to buy that, we just want to assume that this dx0 is 0 actually, because x0 is fixed, we do not want to change the problem basically. So, we need to repeat this procedure until convergence actually. So, that is the thing that we are talking. Now, also remember, because you do not want to compute this do not want to make use of this dx0, then the idea is why to compute this dx0. you need not compute it that way. That means, whatever matrix inverse that you are talking here, that is 2 this matrix inversion that you are talking here is actually a 2n by 2n matrix dimension actually. Okay. And instead of doing a 2n by 2n matrix inversion, if you just do half of this, then obviously you need to do n by n matrix inversion, which can be computationally simpler actually. So, you can save some computations. Once you do that, then you can try to split this phi vector into two sub matrices phi 1 phi 2 like that vertically, and then you can interpret that this dzf that I am talking about can be interpreted that way, and I will take only lambda 2f times d lambda 0 part of it. But remember, lambda 2f is not a square matrix, so I cannot talk about inverse of that. I have to have some matrix which will some matrix which will relate it in a square matrix sense. So, I can take inverse of that. So, for that we can, for convenience, we can write this h which is lambda f. So, that is coming from this boundary condition, that is lambda f equal to the del phi by del x f also the thing like that, and hence I can interpret that this dh that I am talking here, okay, is given as something like that. dh, one side you can see that is directly coming from errors in zf. So, that is what it is, and the other side is lambda f minus lambda f star. Lambda f star is the ideal values for lambda f that the boundary condition gives actually. Okay, so that is the true or desired value for lambda f. So, that is we need to do that, and hence this equation what you see here now, if you go back actually, you can interpret only d lambda f, okay, that is dh actually. Okay. So, what that will happen, that dh by dh, what will happen is something like del h by del z, okay, evaluated at Tf, okay, into phi 2f is equal to dh actually, that is what you will do. Okay. Now, if that happens, okay, no, there is a small mistake here probably, okay, into this lambda, okay, into d lambda 0, okay, is equal to dh. Okay. Then obviously you can solve for lambda 0 d lambda 0 that way actually. You can do this algebra yourself actually. So, make use of this equation and then go back to this equation and then try to extract what is dh, and then that equation will pop up, and hence you can do about this, and this matrix dimension that you are talking is actually n by n. So, instead of doing 2n by 2n matrix inversion, you will be able to do n by n matrix inversion. So, that is the procedure that you can repeat until convergence actually. Okay. So, that is what we do in sorting method actually. So, you started with a lambda 0 and then integrated it forward, and then you saw that there is an error for that, for the lambda f thing. So, using the error in lambda f, you want to correct something in lambda 0, and that is like sorting, gun sorting actually, that is why it is called sorting method actually. So, you need to repeat this procedure until convergence, that is the sorting method. Now, let us go to the last method, which is quasi linearization method. Okay. In this particular one, I will be more interested in talking 2-point boundary value problem in general, okay, and multi-point boundary value conditions in general. Okay. So, they are certainly useful in optimal control solution per se, but we will not go back to that same equation that we discussed, but rather we will discuss in a more generic way. Okay. So, let us see what is the problem. Problem is, we have a set of differential equations, z dot is f of z, okay, z can contain x and lambda, okay, and then there are boundary conditions which are given in this form. That means, C transpose Z I, whatever you are looking at here, is equal to B I, where I t, okay, this I t I, okay, what you are looking at belongs to T, and I stands for n to n actually, 1 to n. Okay. So, it can happen something like, okay, what you are telling here is boundary conditions can be given at multiple time actually. Okay. It need not be given only at initial final, but it can be given at discrete points of time actually that way, and need not be given a specified value per se, it can be given as some sort of a linear combination of those values or those components of z in general basically. Okay. So, it can contain something like linear equations from of both x and lambda together basically. Okay. So, that is a more generic formulation, and let us say how do you solve this actually. Okay. And we also assume that this vector differential equation has a unique solution over this T0 to Tf, otherwise there is a problem for solving this actually. Okay. So, what is the trick? Trick here is this nonlinear multi-point boundary value problem is first transformed into a sequence of linear stationary boundary value problems, and the solution of those problems is made to approximate the solution of the true problem actually. Okay. That means, you break a kind of divide and rule actually. Okay. So, you this entire nonlinear multi-point boundary value problem, you first divide it into a sequence of linear boundary value problems, non-stationary of course, and then the solution you find out for those problem, and then you think that okay, the solution of this problem has to be made approximate, I mean it has to be made equal to the solution of the true problem in an approximate sense basically. Okay, that is what we want to do. Now, how do you do that? Obviously, we start with a guess approximation, that is, let us say z of n is available to us, that is a guess value, okay, and it need not satisfy the boundary condition. It may start with something which exactly may or may not satisfy all the boundary conditions actually. So, obviously, we want to repeat this so that it satisfies the boundary condition essentially basically. Okay, that is the whole idea there. So, for updating the solution, we need to proceed this way. Let us say we linearize this equation, z dot is f of z t, and then that is what we get. Again, the similar way what we discussed, del f by del del turns out to be a of t, and this a of t, okay, and this delta z n by definition is z n plus 1 minus z n basically. So, what you are looking for is, you have nth iteration value known to you, this capital N is an iteration number sort of thing, and then n plus 1 is something that you want to find out actually. Okay. So, for that the error equation is like this, which is a time varying linear equation again, that is what we are talking actually. Now, in the boundary condition sense, this is the boundary condition. So, let us plug it back whatever. So, the boundary condition is not satisfied at n, but we want to make it satisfied at n plus 1 at least actually. So, if I substitute this condition as n plus 1 solution, then at least I should be able to satisfy the boundary condition, and that is what I am aiming for actually. So, C of T I into inner product of z of n plus 1 T I, that has to satisfy equal to V I, but you know this z n plus 1 T I is nothing but this one actually, z n plus delta z n. Okay. So, if you look at, if you want to see this, I mean this linear inner product is a linear operator, and you expand it into two terms, and you say okay, C I I mean C of T I into delta z n of T I is nothing but negative of that plus V I actually. So, I can interpret this same, I mean this condition from this equation as well actually. So, that is what I do here. Now, from the linearized system dynamics, what you want to do, I mean if you go back to this linearized system dynamics, again you substitute this definition, okay, then you can say okay, z n plus 1 dot is nothing but this guy, because this one minus this one is that, by that is what we have here. So, making use of the definition, we are telling okay, z n plus 1 dot is nothing but this one plus this one. So, obviously, it gives you some sort of a homogeneous part, and then there is a forcing function actually. Okay. So, if there is a homogeneous part, there is still a linear equation by the way, okay, this n plus 1 sense. So, this linear equation you have a solution which is given as like a homogeneous solution and a particular integral actually, a particular solution. So, this z n plus 1 is the direct solution that I am looking for. So, remember I started with z n, but I am looking for a solution in terms of z n plus 1, okay, and hence I am interpreting all these equations that are available to me basically. Okay. So, I have this z n plus 1 dot, which is something like this, a part of that is homogeneous expression, homogeneous equation, and part of that is actually a forcing function basically. Okay. So, now the solution of the above equation is certainly this one through a state transition matrix again basically, and again this state transition matrix satisfies these conditions actually. Now, what is the thing here? If you observe this equation, we have the form ready now, right? This equation what you have here, okay, we have the form of the solution ready basically. Okay. Now, what you really need is how to build on this actually, like how do you find out this, how do you find out this, and how do you find out that. I mean that is what once you know that, then the solution is ready anyway basically. So, here you are telling how do you find out this, and that is coming from this, because this is the state transition matrix which will satisfy the same differential equation, and the boundary condition is independent of any other condition. So, this can be integrated separately to get this basically. Now, what about these two basically? Okay. Now, this particular solution P n plus 1, I am talking about this one now, okay, can be obtained by observing that it satisfies the same differential equation. Any particular solution should satisfy the same differential equation actually. So, then you put it back and then see okay, in the same differential equation sense what happens, because that is my solution anyway, right, this entire solution. this entire solution I will put it back in my differential equation solution what I have there, and then I tell okay all these equations are known to me, because this state equation, okay, what is happening here is this equation as I know will cancel out, this one will cancel out with this one. Okay. So, because that is the condition that will come from here basically, this condition what you see here, okay. That condition will help me in cancelling out that first two terms, and you are left out with that one. So, you have a differential equation for this guy, this p n plus 1 t, but you also need a boundary condition for that. This is the differential equation. So, the boundary condition for that comes from this condition what you have here, z n plus 1 is nothing but this by definition, and this is identity of course. Okay. This is identity, then what happens, this cancels out again. Okay. This one goes to this one. So, you are left out with the condition that p n 1 plus p n plus 1 t 0 is actually 0. Okay. So, you have a differential equation for p n plus 1 and you have a corresponding boundary condition also, and that is how you solve this particular thing basically. Okay. Now, what about the rest one? This is I mean I still need to have this condition to have a solution of that, and that condition I will go back and say okay the boundary condition of this I know this is my boundary condition that I want to satisfy. So, I put it back my solution form, this is my solution form actually. Okay. So, that one I will put it back in this boundary condition that is given to me, and then again this inner product is a linear operator and all that. I can split this equation in two parts, and then I can tell okay this is this inner product in the left hand side is nothing but equal to this inner product negative sign with this plus bi term basically. So, that means this condition on this n plus 1 is available to you, it is not explicitly available to you yet, but these are a set of bunch of linear equations, and hence you can solve this linear set of linear equations to get this z n plus 1 at t 0, and hence every component of that is ready. So, we had an idea how to compute this okay, through this equation, we have an idea how to compute that through this set of equations, this equation and this equation, and now we have an idea of how to compute this z n plus 1 t 0. So, if this equation if you look at it, we have all the building blocks ready now. So, we have everything that is in place basically. So, we can compute this z n plus 1, the updated control basically. Okay. So, that is how this procedure operates basically. Now, there is a very neat convergence property of this quasi-linearization method, which which also actually tells that so this theorem reads something like that. Okay. So, under the solution, under the assumption that the problem admits a unique solution, that is what we wanted in the beginning, remember that as one of the assumption was the between t 0 to t f this problem has a unique solution. So, if you under that assumption, okay, it can be shown that the sequence of vectors, okay, that is what you are computing in an iterative sense, that the sequence of vector will actually converge to the true solution, that is the first guarantee, it will converge to the true solution actually. Okay. Once that guarantee is in place, then we want to ask the questions at what rate actually, and that guarantee is also there, that tells that the process can be shown to have quadratic convergence in general. That means, in a norm sense it has to decrease that way, which is extremely good. Also remember Newton-Raphson technique also satisfies some of these quadratic convergence properties and all that. So, what it tells is the convergence can be very fast actually. Okay. So, every successive iteration norm of that will be less than equal to some positive constant and the difference of the two previous values. Okay. I want an update value, let us say z n is my current value actually, I want an update value. So, I have an error with respect to my previous solution and I have an error with respect to my updated solution. Okay. Now, with the error with respect to the updated solution is certainly guaranteed to be less than equal to some constant times the error in the with respect to the previous solution. So, that is what it tells actually. So, that way the convergence can be fast actually, quadratic convergence tells you like that. Okay. And furthermore, for a large class of systems it can also be shown to have monotone convergence as well, which is extremely good. In addition to quadratic convergence, monotonic convergence means it will converge from one side only. If you start with a positive number, it will decrease and go to 0. It will never overshoot and then oscillate around 0 and then converge. That is monotonic convergence actually. So, you can see that there are multiple levels of guarantee here. One is it will converge to the true solution first, and not only it will converge at a quadratic rate, and it will also converge in a monotonic sense basically. Okay. So, it is extremely powerful method in my view in that sense basically. So, you can try some of that and then have a feeling yourself actually. Now, before I conclude, I will also suggest that you solve this particular problem using sorting method as well as quasi-linear regression, then you will have some sort of a feeling of what goes on. This is actually a very small problem, but it certainly give you some feeling. So, this is a quadratic cost function x square plus y square dt, but this is not a linear state equation, it is a minus x square term is there, certainly is a non-linear differential equation. We have initial condition like that and you want to minimize that with this cost function, I mean all the necessary conditions of optimality you can derive very easily basically, because the cost function something you know. So, Hamiltonian is L plus lambda f, because lambda is one scalar again, because state is also scalar. So, you have this half of x square plus e square plus lambda times this one minus x square plus u. So, that is what it is. The state equation is already known to you, okay, x dot equal to del s by del lambda, but lambda is del s by del lambda is like that, which is again the same thing. So, that is state equation. Then the optimal control equation is del s by del u equal to 0. So, del s by del u means one term is u plus one more term is lambda. So, lambda plus u is 0. So, u equal to minus lambda. Co-state equation is lambda dot equal minus del s by del x. So, if you take differentiation of h with respect to x, then this is x, one x term coming here minus of that, because there is a minus sign here, and then there is a minus 2x lambda which will become plus 2x lambda basically because of this minus sign. So, you have x dot is that, u equal to that, and then lambda dot is that. Boundary condition sense x of 0 is known to you, and lambda of 1, remember T f equal to 1 here, where that is what you have taken, and lambda of 1 is del phi by del x, evaluated at 1, but phi is 0 anyway, there is no phi term. So, that is 0 basically. So, you have this condition which tells you that x dot is that, and x dot is minus x square minus lambda, because u is minus lambda. So, this particular plus u I am substituting by minus lambda basically already. So, that way the optimal control equation is already used actually. So, you have this state equation that way, and you have co-state equation, you have a 2-dimensional problem now. So, that means that z that we discussed here, okay, in this problem, z is nothing but 1 x and 1 lambda, 2-dimensional vector, and you have the corresponding boundary conditions known to you given at 2 different time. So, you can try to solve this problem using sorting method as well as quasi-linear method. That is what I will suggest you to do that by yourself, using a small, writing your small program files in whatever language you want to do, and then have a feeling by plotting these results and things like that. So, that is what I will suggest. Now, references, there are numerical method sense, some of these things I have taken from Kirk book, especially the gradient method as well as the quasi-linear method I have taken from there. And sorting method is I do not know, I mean I have taken from this one, and it can be available in many other books also by the way, sorting method. And then the Bryson and Hu is a standard optimal control book, there are many numerical methods as well, and then this is also a good book in my view, okay, even though it was written almost parallel to Bryson and Hu sort of thing. So, one is 75, one is 77, but that is okay. So, these are some of the references that you can see for more details on this method, and these are some of the 2 survey papers, very classical survey paper. One is very old, which talks about 66 and all that, but it is a very nice paper, talks about many status of the optimal control theory and applications at that point of time 36. So, it gives us a very nice feeling of what happened initially. On 94 there is a very neat survey paper again, which talks about real life control problem, how will you use some of these practical solutions using many practical kind of numerical methods and things like that. So, I suggest that you read some of these to have a better feeling of that. So, I will probably stop here. Thanks for that. Thanks a lot for the attention.